Good morning, all of you. Good morning, everyone. I am Dr. Sachin V. Mukhamale, Head and Assistant Professor, Department of Physics, Sri Pundalik Maharaj Mahavidyalaya, Nandura. It is my great pleasure to give uh, Dr. C.V. Raman Physics lecture series on behalf of this occasion of National Science Day. So, first of all, I am thankful to Principal Sri Shivaji Science and Arts College Chikli and organizing committee of this lecture series to give a chance to deliver a lecture on this free electron theory. Okay, today we are giving a lecture on free electron theory. So in this lecture, now I am going to start the lecture. So we have to focus only on free electron theory. Okay, free electron theory. Now I am going to introduce about the introduction about free electron theory in solids. For example, suppose we have a solids. Okay, we know that three states of matter present in the universe: solid, liquid, and gases. We are focusing only on the solids. Okay, the free electron theory is related to the metal and non-metal. Okay, in the solid, electron in the outermost orbit of the atoms determine the electrical properties. Okay, we know that according to Bohr's postulate, electron revolve around the nucleus. Is it correct? Outermost electron is responsible for the electrical properties. So we are going to discuss here electron theory is applicable to the all the solids, both metal, non-metal. Okay, in addition, it explains the electrical, thermal, as well as magnetic properties of the solid. The structure and the properties of the solid are explained and employing their electronic structure. Okay, we know that the electron configuration, but electronic structure is differ from the electronic configuration. Okay, electronic structure is related for the solid state. So we have to discuss this electron theory by using classical mechanics. We can simply say that classical free electron theory, another quantum free electron theory, and zone theory. When we are going to understand the free electron theory, we are going to use these three theories. First, classical free electron theory. Second, quantum mechanical free electron theory. Third, zone theory. Okay, classical free electron theory. Okay, this theory was developed by Drude and Lorentz in 1900. According to this theory, metal contains the free electron. We know that if you see the band structure of the metal, the conduction band and valence band both are the overlap. Is that correct? There is no energy gap. In this in this metal, there is a free electron. Outermost electron revolve around the nucleus. This outermost electron is responsible for the free conduction. Okay, and this free electron which are responsible for the electrical conductivity and the electrons to obey the laws of classical mechanics. And the quantum free electron theory in 1928, Sommerfeld developed this theory, quantum free electron theory. According to Sommerfeld, the free electron move with a constant potential. The free electron move in a constant potential. Constant potential means V of x. We know that V of x is the potential. We have learned the potential wave, infinite potential wave, definite potential wave, represented with capital V of x. These electrons are move in constant potential. So this theory obeys some quantum laws. Okay. In zone theory is the band theory of structure. In band theory of structure, we are going to use the zone theory for the free electron. In the free electron theory, Bloch introduced the band theory in 1928. According to his theory, free electron move in a periodic potential provided with the lattice. consider the free electron in periodic potential, there exists energy versus momentum k vector. Okay, there is a possibility of the highest maxima of the valence band and lowest minimum of the conduction band. According to the band theory of the solid, we can define the origin of the band gap. Okay, and there is also, we have seen that this is the highest maxima of the valence band and the lowest minima of the conduction band. Okay, so in this case, if you are going to observe this highest maxima of the valence band and this lowest minima of the conduction band, and both lie on the same in both lie on the same energy versus momentum k vector. Okay, there is a possibility of the transition of the electron from valence band to the conduction band. This is the zone theory. Okay, so we have to understand the free electron theory. So we have to require for some assumption. What kind of assumption to understand the free electron theory by using classical mechanics? And Drude and Lorentz assume some assumption of free electron theory. Okay, what is the first assumption of that? Okay, in metal, we know that in metal there is a large number of the free electron. Okay, suppose if you take the copper 29, there is a number of free electron in outermost orbit. We know the electron configuration, is that correct? So that in metal there are large number of free electron moving in freely in all possible direction. This is the first assumption of the free electron theory. Okay, second, this free electron behave like a gas. Similar assumption we are going to consider kinetic theory of gases. Is it correct? The gas consists of large number of tiny particles, perfectly elastic nature, then called as the molecule. The similar way, free electron behave like the gas molecule container, obeying the laws of the kinetic theory of the gases. The second assumption. This is second assumption. In the absence of the field of the energy associated with each electron at the temperature capital T, at the temperature T, whatever at the room temperature, higher temperature, low temperature. Okay, in the absence of the field energy associated with each electron at a particular temperature, at a particular, I am going to say here particular temperature T, is given by 3 by 2 kT. Okay, the gas, if you are going to consider the gas as 3 degrees of freedom, we are going to carry that degrees of freedom of the gas molecule has, according to equipartition theorem. Okay, every gas molecule has equipartition, according to equipartition theorem, says 1/2 kT. Okay, according to 3-dimensional molecule, it can rotate in 3-dimensional, 1-dimensional, 2-dimensional, 3-dimensional rotation of the gas molecule. The electron, we are going to by considering the assumption of this 3 by 2 kT energy. It is related to kinetic energy. This 3 by 2 kT is related to the 1/2 mv square energy. That v square is the thermal energy. If you are giving the heat energy, heat is transferred in the form of convection. If you are going to consider the gas, so that it is transferred through convection process. So that 1/2 mv square compared to the 3 by 2 kT energy. This is third assumption. Okay, and that k is the Boltzmann constant. In the metal, the positive ion cores at a fixed position. We know that in metal, the positive ion core, and positive ion core, where we know that positive ion core is the fixed position, and the free electron move in randomly and collide with the positive ion core with other free electron with the bond rays, and hence this collision is elastic. Is related for the similar for the kinetic theory of the gases. Yes, kinetic theory of the gases. Therefore, the electric conduction is due to the free electrons only. Okay. Fourth assumption. In fourth assumption, what they are going to consider in metal, the positive ion cores at the fixed position. Positive ion cores. Suppose if I draw the positive ion cores. Positive ion cores. Suppose this is the positive ion cores. This positive ion cores here, 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 here. So this positive ion cores, okay, at the fixed position, the free electron move in outermost orbit. Okay, they can move in randomly manner according to the assumption of kinetic theory of this free electron theory. They are randomly moved. They can possibly collide with the positive ion core. What I'm going to say here, ion core. This is the ion core. Positive core potential, that there is a possibility to collide with the core. There is possibility to collide with here. Possibility of the core. Okay, ion positive ion core. Hence, this collision are the elastic, perfectly elastic. Therefore, the electrical conduction is due to only free electron only. Fifth assumption of the kind, fifth assumption of free electron theory is the electron velocity in the metal obeys the Maxwell-Boltzmann distribution of the velocity. If you are going to consider the electron are moving in a randomly manner, it has some positive velocity. That velocity of free electron satisfies the Maxwell-Boltzmann distribution according to classical mechanics. Sixth assumption is that the free electron move in a constant potential field. V of x is the constant field. Okay, move in a constant potential field. Hence, the potential energy of the constant potential of the electron is always constant. Okay. When the electric field is applied to the metal, suppose we have a metal. Suppose if you take consider this is the metal or metal, this is steel, not a metal. But if you are going to consider the metal and if you are going to apply the electric field to this metal, the free electron are accelerated in the direction opposite to the direction of applied electric field. We know that one. We have learned that one. Any free charge presence of electric field explains the force. Okay. The flow of the direction of opposite to the direction of applied electric field. Electrons are accelerated in presence of electric field. Is it correct? Electrons are accelerated in the direction opposite to the applied direction of applied electric field with a velocity v, and that velocity called as drift velocity is represented by the capital V suffix the d, the drift velocity. Okay. So these are the basic assumption. Basic assumption means assumptions of the free electron theory, the classical. Okay, classical concept. Here, these assumptions are made by Drude and Lorentz. Okay. What are the merits and demerits of the classical free electron theory? Merits. Now we are going to discuss the success or advantages of the merits classical free electron theory. Suppose we have a metal semiconductor contact, or if you are going to consider metal contact, okay, and if you are going to take the IV characteristic of that metal substrate, and we are going to observe that IV characteristic shows the, if you plot the current along the y-axis, voltage along the x-axis, and if you apply some bias to that potential of the substrate, okay, so we are going to observe that IV characteristic shows the Ohm's law. Okay, ohmic contact, or simply it verifies the Ohm's law in free electron theory. Most of the free electron theory obeys the Ohm's law. Second, it explains the electrical and thermal conductivities in the metal. Okay. Third, success advantage, or it derives the Wiedemann-Franz law. It is a ratio of thermal conductivity to electrical conductivity. It explains the optical properties of the metal. Okay. These are the merits. And what is the limitation of this free electron theory? It fails to explain the electrical conductivity of the semiconductor and insulator. This theory is not going to applicable for the semiconductor. Okay, it fails. First limitation of this theory, it fails to explain the electrical conductivity of the semiconductor and the insulator. Second failure, it fails to explain the temperature variation of the electrical conductivity at low temperature. It fails to explain the concept of the specific heat of the metal. Okay. Fourth limitation, it fails to explain mean free path of the electron. Fifth failure, the phenomena like photoelectric effect, quantum effect, blackbody radiation could not explain by the classical free electron theory. Classical could not explain the photoelectric effect, quantum effect, blackbody radiation. This phenomenon explained by the quantum mechanical theory, and this is the start of exact birth of the quantum mechanics, origin of the quantum mechanics, to start from this blackbody radiation, photoelectric effect, quantum effect. Okay, these are the failure. And last failure is that it fails to explain temperature dependent paramagnetic susceptibility of the ferromagnetic material. Okay, now we have seen here assumption of free electron theory. Okay, and another merits and demerits, advantages and disadvantages of failure we have seen it. Now we are going to discuss about the quantum mechanical free electron theory assumptions. Okay, First, we understand quantum free electron theory. Quantum free electron theory was proposed by Sommerfeld in 1928. This why this theory is developed. This theory is developed due to this theory overcomes many drawbacks of the classical theory. Okay, Sommerfeld explained by choosing the Fermi-Dirac statistics. In the classical mechanics, we have seen that classical free electron theory assumptions that electron possess the velocity, that velocity obeys the Maxwell-Boltzmann distribution. Okay, but in quantum mechanical free electron theory, it's obeys the Fermi-Dirac distribution. Okay, applying the principle of the quantum mechanics. What is the assumption of quantum free electron theory? The valence electron move valence electron, those electrons present in the valence band, these electrons are freely moving in constant potential within the boundaries of the metal and is prevented from escaping this free electron in the metal at the boundaries of the potential. This constant potential with high potential, this is high constant potential. Okay, and the electron is trapped in this potential well. Okay, means the valence electron move freely in constant potential with the boundaries of the metal and is prevented from escaping the metal at the boundaries high potential. Hence, the electron is trapped in potential well. Why we are going to confine the electron potential well? We have to consider the constant potential well, the valence electron in constant potential well. It means that electron are confined. Okay, electron is confined in trapped potential well. Trapping. This is quantum mechanical phenomenon. Okay, the distribution of the electron in various allowed energy level. The distribution of electrons in various allowed energy levels occurs per Pauli's exclusion principle. We have learned in statistical mechanics Pauli's exclusion principle. Okay. Third assumption is the quantum mechanical theory. The attraction between the free electron and the lattice ion and the repulsion between the electron themselves and ignored. Okay. The attraction between the free electron and the lattice ion core and the repulsion between the electron themselves are ignored. The distribution of the energy among the free electron, distribution of the energy. What kind of energy? That distribution of free electron. Okay, those electron are the free, belongs to that constant potential well, a electron trapped in that distributed free electron energy according to Fermi-Dirac statistics. We have to fill up that. Okay, no two electron can occupy the same state. Okay, the energy values of the free electron are quantized. Okay, this energy of the values, energy values of that free electron are quantized according to quantum mechanics. Okay, it means that all the electrons are trapped in, it means that the bound state of that electron, this bound state of the electron are trapped. It means that this is the bound state and every bound state has quantized energy levels we have observed. Okay, now so that bound state energy level of the electron equals to n square as dragon square at ml square. We know that energy relation of this. If you are going to observe that energy, if you are going to see here, so that energy we have learned that. So electron trapping potential will we have to find out that energy level En equals to n square s square at ml square, n square h square divided by 8 ml square. L is the width of the trapping of the potential well, where n is the levels of that. En equals to 1, 2, 3 quantized energy level, principal quantum number. So what are the merits and demerits of the quantum free electron theory? Now we are going to discuss here. Merits means if you are going to assume that quantum free electron theory, from this theory it is successfully explained the electrical, thermal, conductivity of the metal. that is successfully explains the electrical thermal conductivity of the metal. This theory successfully explains electron thermal property by using the quantum mechanical theory. It can explain the thermionic emission phenomena. Thermionic emission phenomena, Richard-Dushman equation. We understand that field emission. We understand field emission. There is a number of emission. It can explain the thermionic phenomena. Okay. Joule-Rating effect, Richard-Dushman equation, thermionic emission. It explains the temperature dependence of conductivity of the metal. It explains the temperature dependence of the conductivity of the metal. It can explain the specific heat of the metal. It explains the magnetic susceptibility of the metal. It can explain the photoelectric effect, quantum effect, and blackbody radiation. It gives the correct mathematical expression of thermal conductivity of the metal. Okay. There is also demerits of the quantum free electron theory. It is unable to explain the metallic properties. It unable to explain metallic property exhibited by the only certain crystal. Okay, crystal properties. It is unable to explain. Quantum mechanics could not explain the metallic properties. Okay, it is related for the crystal. It is unable to explain why atomic arrays in the metallic crystal should prefer the certain structure only. Why atomic arrays in the metallic crystal should prefer the certain structure only. This theory fails to distinguish between the metal, semiconductor, unable to explain. This theory unable to explain the distinguish between metal, semiconductor, and insulator. It also fails to explain the positive value of the Hall coefficient. According to this theory, only two electrons are present in the Fermi level. According to this theory, only two electrons are present in the Fermi level, and they are responsible for the conduction. They are responsible for the conduction, which is not a true. No, only two electrons are present in the Fermi level, and these two electrons are responsible for the electron. Means these are the field level. Okay, so we are going to discuss that Fermi energy level also in this session, but we will see here it is not required only two electrons for to understand the conduction phenomena. Now we will see the electrical conductivity, derivative. Now we will see derivation of electrical conductivity. Okay. Now just see here. Look at this. Just I'm going to take the chalk here. Just hold on. Just 1 minute. Yes, I got the chalk here. See here. Expression for the just 1 minute. Just take the image back side in this manner. Now you look here.